This is the third video in this playlist about the counting principles and counting problems. In the first two videos, we have already covered the principles and then the shortcuts, and then we also talked about overcounting. So right now, it's going to feel like I'm drastically changing the subject for a few minutes, but I ask you to bear with me because I do have a reason to be talking about these things. So here's something else. You have probably heard this story before, but I do want to say all the things again, if anything else, just to establish the vocabulary. So what is a function? A function is a rule to associate elements of a set A to elements of another set B. So for example, this element is going to be associated with that one, this element is going to be associated with that one, and so on. The rule can be any rule, so I can draw any arrows that I want. The notation goes like this. F is a function going from A to B. A is called the domain of the function. The set A is the domain of the function where the arrows begin. And the set B is called the codomain of the function. Now, at this point in the story, a lot of people are surprised because they were expecting the word range, but just bear with me for a minute because the word range will appear. The thing that I've drawn so far is not really yet a function from A to B because I have elements in my domain that are not doing anything. So I can't have that. In order for something to be a function, then every element of the domain needs to be connected to some element in the codomain. It can be like this, for example. So if you draw two sets and some arrows, but there are some elements in A that are not connecting with anybody, then that's not called a function. And as you can see, I've done some weird things in the set B. This guy has not received any arrows. These three guys are the subset of B that have actually received some arrows from A. So that is the range. The range is the subset of the codomain that actually receives some arrows from the domain. Notice that there is no reason to make this distinction in the left side of the picture, in the domain, because being a function itself already says that the whole of the set A, everybody in there is connecting to somebody. But there is no rule like that for the codomain. So there we actually do need two different words, which are range and codomain. The codomain is the whole set, it's the set itself, and the range is just the part that is actually connecting to somebody. But when you would look at the left side and the whole set and the elements that are actually connected, that's the same thing because everybody needs to be connected in order to be a function. Now, of course, it's also interesting in the right side of the picture in B when those two things are the same, when every element of B actually connects to somebody from A. That is interesting. It is interesting, so it receives a name. This is called a surjective function when the range is equal to the codomain. That is just a shortened way of saying that every element in the codomain is actually connected to some element from the domain. I could have written this whole sentence, but instead I just wanted to use the vocabulary. And there is something else in the picture that's also different between the way A and B look, because some elements of B are not receiving anybody like we were talking about, but also some elements of B are receiving more than one arrow. And this doesn't happen in A. Each element only has one arrow. And in fact, I should have written this down in the definition. When I said it's connected to some element, I should have said instead that it is connected to exactly one element. So let's make that change here. Exactly one element does say that it is connected to somebody because it's one somebody, but it also doesn't allow for there to be two somebodies because it's exactly one. So we could also give a name for what happens when this doesn't happen in B. Like in this case, there are points that are receiving two arrows, but when there aren't, that's also an interesting case and it receives a name as well. So no element of the codomain is connected to more than one element from the domain. This is a different way of saying the sentence from the way that the function definition is stated, because it is different. Here, I do want to allow them to receive nobody, okay? I just don't want to see anybody receiving two, but receiving none is okay for the function to be injective. So like this is injective. That last guy is not receiving anybody, but that's fine because everybody who is receiving an arrow is just one arrow. So the first of these pictures is injective, but it's not surjective because of the element that didn't receive anybody. And the second picture is surjective because everybody received an arrow, but it's not injective because one of the guys has received two arrows. So it's pretty common for people when they are learning these concepts to be confused because you have two sets, A and B, and you have two names, surjective and injective. So it is natural for you to expect these definitions to be a mirror of each other. Like they're going to say basically the same thing, but one of them is saying it about A and the other one is saying it about B. This expectation is what causes this to be a confusing set of mathematical terms, because that is not the case. Injective and surjective are not a mirror of each other. Both of them are statements about the codomain. There is no equivalent statement about the domain. So you're expecting a mirror that isn't there. The only statement about the domain is the definition of function. Function, each element, one arrow. One element, one arrow. That's it. The domain is always going to be like that. But the codomain can be a lot more interesting. So that's why we have these two words to talk about the codomain. Surjective is when everybody is covered, and injective is when nobody is covered more than once. Of course, I'm giving you examples here in these pictures of functions that are one but are not the other, or are the other but are not the one. But of course, some functions are neither, like the first example that I gave you. And also there are functions that are going to be both. That is also interesting. That also receives a name. A bijective function is one that is at the same time injective and surjective. So in this case, not only every element in the domain has its own unique arrow, but every element in the codomain in this case is also going to have its own unique arrow. Now, before I tell you why I'm talking about any of this today in a video about counting, let me talk a little bit about where we usually hear this story and why I don't think that's a good idea. We usually hear this story when we are very young and we are first being introduced to the concept of functions from R to R. So we are going to spend a little bit of time just looking at generic functions like this, seeing if we can graphically identify, like here's the number 6. So what is f of 6? Oh, it's this point here. So f of 6 is equal to 2 in this crazy graph. And then after we spend a little while doing that, we are going to be introduced to specific functions. We are going to spend a long time talking about linear functions. We're going to talk about the slope, the rise over run, the y-intercept, and we spend a long time talking about that. And then they introduce us finally to all sorts of different functions. There are quadratic functions, there are exponential functions, and I absolutely love talking about all of these things. But that's not what we're talking about today. And this also seemingly bears no resemblance to what we were just talking about. For a very simple reason. This whole conversation that we were having, I had 5 elements in A, I had 4 elements in B. When you heard the story for the first time, I bet your teacher also drew a very similar picture with a handful of points on the left and a handful of points on the right. And you spent a long time talking about that in order to go ahead and talk about this, where both the domain and the codomain are not finite sets of half a dozen points. They're not even discrete sets. They are continuous sets. They're the real numbers. So why were we talking about this if it in no way resembles this? Of course, the concepts are there. I'm not saying that it's crazy, no, but the concepts are here. A quadratic function, for example, doesn't reach everybody in its codomain. It has a limited range, so it is not surjective. And by the way, it's also not injective because the same element of the range is receiving 2 arrows. You see, where are the arrows? The arrows are the points. A point in the graph of a function is an arrow from this value in the domain to that value in the codomain. So that's also not injective because it is receiving 2, right, from this point in the domain and also this point in the domain. So that's not injective. And we could keep talking about this, but I don't want to because I want to go back to talking about counting. I want to go back to talking about finite sets. I'm not interested in the real numbers right now. So I do like both of these topics. I like the real functions, and I also like these concepts of injective and surjective, but I don't think they are interesting for the same reasons. I don't think that this helps at all in understanding this. So I don't like talking about it then, but I do like to talk about it now because the place where this is interesting is when the sets are finite. Because being surjective, being injective, impose restrictions on the number of elements of the sets A and B. And when I talk about number of elements, now I'm finally starting to talk about counting because it's the number of things. So if a function is going to be surjective, if it's going to cover every single point in the codomain, then the set A, which is the one on the left, needs to be at least as big as the set B. So I need 4 points here to cover those 4 points, but maybe I have some extra points and I am covering some elements of B twice because that's just surjective. So in that case, I need the number of elements in A to be at least as big as the number of elements in B. And if I want my function to be injective, then it's going to be the opposite because I can't put 2 arrows in the same place. So the most arrows that I can put is the number of elements that I have in B, but I don't have to cover everybody to be injective. So the number of elements in A in this case can be less or equal to the number of elements in B. But if my function is going to be bijective, then it's 1-to-1. Then the number of elements in the set A is the same as the number of elements in the set B. And this is interesting because I want to count. I am talking about counting. So say that I want to count the number of elements in set A, but it just happens to be easier to count the number of elements in set B. But what if I know there is a bijective function between those two sets? So I know that they have the same number of elements and I can choose to count something that is easier. Now I'm going to give you the most traditional example for you to understand exactly what I'm talking about. Okay, so here's what we're gonna do now. I have 5 boxes of different Nespresso pods and I wanna pick 10 of them to put in this big mug. They can be the same color or different colors, it doesn't matter, but I do have 10 of each because these are brand new boxes. So there are basically no restrictions besides 5 different types. 10 pods to go in the big mug. It can be all 10 red, that's a possibility, or it can be 2 of each. That is the number of things that I want to count now. In how many different ways can I pick the 10 pods to put in the big cup?
I think I'm addicted 'cause you got me shaking from the caffeine. Oh, it's burning hot, but I could pour myself a dozen cups.
Okay, so here they all are. You can clearly see the difference between all 5 types, right? There's 5 clearly different colors. Okay, so how are we going to do that? Because I've been telling you that for every difficult problem, you have to break it apart into smaller questions. So maybe one possibility would be to start by asking how many pods are going to be red? There are 11 different answers for that questions because it can be no red pods at all or 1, 2, 3, all the way to 10. So that's 11 possibilities. Let's say that I say 3. There's 3 red pods. There they go into the cup. But now we have a problem because next we want to choose how many gold pods go into the cup. And I have already put 3 red ones in there. So I have 7 empty spaces, which means that I have 8 possibilities for the gold pod, which can be numbers from 0 to 7. But if instead of 3, I had put 4 red pods, then I have 1 fewer space. So instead of 8 possibilities for gold, I only have 7 possibilities. That is not looking at all like multiplication principle. In fact, it's just the opposite. Each different number of red pods that I put gives me a completely different number of possibilities for gold pods. So it would have to branch out in a big tree. And worse than that, because when I put the gold pods and now I have to make the same choice for the gray ones, my tree just keeps branching out. So this is a terrible idea. This is not how we're going to solve this problem. So here's the thing. Some students love asking about, does the order matter, right? And we've already discussed in the previous video how in the case of coffee, the order does not matter. But if I was picking the 10 pods to put back into one of the boxes instead, then you could say that the order matters, because the box is like a row, right? So if I say that the red pods are going to go in first, there's 2 of them there, and now I'm going to put 3 gold pods in there. Well, between them, the order doesn't matter. And I guess it's not so much that the order matters, but it is that I have decided on the order. I'm always putting the red ones first and then the gold and so on. So I don't need a box for that. I can do that on the table. There. I've decided that this is my order. Red, gold, gray, white, and brown. This is 10 pods, so this is one of the possibilities. And here's the thing, it's not that the order matters. The order obviously doesn't matter. They're all going to get together into the big cup anyway. I am just choosing in which order I am going to physically put them in there, just because that can make it a little bit easier to count. So I have decided, this is not a restriction of the problem. This problem doesn't have an order restriction. This is a decision that I'm making. It's not a restriction. I have decided to go in this color order, which is something that I am allowed to do because the problem doesn't restrict it. So in this order, the pods are going to go into the cup. There are 10 of them. It didn't have to be these. It could be different amounts, for example. But whatever amounts they are, I am always going to put them in this same color order, okay? So if I take one away and want to put it back, then it has to be in this order. And more than that, I have 5 colors, so I am going to make my life even easier, and I'm going to separate them with spoons. So after the 3 red pods, I'm going to put a spoon right here. And then between the gold and the gray, there's going to be another spoon as well. There, 10 pods and 4 spoons. That doesn't change the number of different ways in which I can do it. It just takes each way and organizes it in a more systematic way, which hopefully can make counting a little bit easier. I imposed an order. I said red, orange, green, blue, and purple. Notice that I didn't take any blue in this example, but that's fine. And then I said that after putting them in order, I'm going to put some sort of separator. So there's a separator between red and orange, separator between orange and green. There's one here between green and blue, and another one between blue and purple. So that's why there are 2 right there. So I'm always going to have in this sequence 10 pods and 4 separators. The bijection here is happening because any set of 10 pods that I pick up, I can always take those pods, organize them by color, and then put the separators in. That is, this arrow is going from a pod to a sequence. That is a predetermined sequence of steps. There's not 2 different sequences that are going to come up when I do this process. It's just going to be always in the same order and always with the same separators. So it's just one arrow going that way. There is no 2 arrows. And there also isn't the possibility of not being able to do that. So it's exactly one arrow. On the other hand, if I receive a sequence first, a sequence that has 10 pods and 4 separators in some order, like this one, now I'm trying to do the reverse arrow, okay, from a sequence to a set of pods. How am I going to do that? Well, I know that I said that the red ones would always come first from the beginning of the sequence until finding the first separator. And then after the first separator, they are supposed to be orange until the other separator, and then green until the next separator. Now they're supposed to be blue after the next separator, but there's nobody there, so I'm not going to paint anybody blue. And then after the last separator, everybody is purple. So I have now painted the same sequence. I am always able to do that with the sequence and the colors. And whenever I do it to the same sequence, it's going to come up with the same answer. So there's also not 2 arrows going that way. It is a bijection. For each set of pods corresponds a sequence, and for each sequence corresponds a set of pods. So it is a bijection. Set A of the sets of pods has the same number of elements as set B, which is the set of sequences, and now I want to count the sequences. But counting the sequences is so much easier because the sequences always have 10 pods and 4 separators, so that is 14 things. Out of these 14 things, 4 of those are separators. So the only thing that changes is the order. Do the pods come first and then the separators, or the other way around? How long does it take to find the first separator is going to determine how many pods are read, and so on. So in how many different ways can I make a sequence of 14 things out of which 4 are separators? So, well, that is 14 choose 4, which is a very easy number to calculate. It's easy because there is a formula for it, which begins by canceling out both of the 10 factorials. And now let's see what else I can cancel. 4 times 3 is 12. 2 cancels with 14. I have a 7 there. 7 times 13 is 91. 91 times 11 is 91 plus 910, which is 1001. So that's the final answer to the problem. In how many different ways can I pick 10 pods out of those possible colors?